Hello everyone, this is Martin again. This video is the follow-up to the beginner's derivation of E equals mc squared I released about 2 weeks ago. That was a high-level view using Einstein's famous thought experiment, which analyzed the behavior of a photon in a box in deep space. This video is an intermediate level derivation of the famous energy-mass equivalence equation. I will derive E equals mc squared using the work-energy principle, force and momentum, force and energy, and relativistic mass. Two concepts will be used without derivation, in other words they'll be assumed, and that is the Lorentz transformation and the equation for relativistic mass. These will be derived in a later video so as not to complicate the basic theory. Okay, so starting with the work-energy principle. The work-energy principle states that the work done by forces acting on a particle equals the change in the kinetic energy of the particle. Work equals force times the distance over which that force is acting. As stated above, work equals change in energy. So work equals dE, the change in energy, which equals force times the change in distance. Or integrating both sides, we get energy equals the integral of force times the change in displacement, ds. I'm going to put up notes every now and then. Most people will know all about calculus and some people won't. So just not intended as a lecture on calculus, but just to get us through the equations, I'm going to point out a few highlights. dE, delta E, is the rate of change of energy. The integral sign, S, this giant S here, will transform the rate of change, or differential, to its constant value. So the integral of dE equals E. So if we're integrating both sides, we will have the integral of dE, which is E, equals the integral of f ds. And we're going to remember this one as equation 1. Now we're going to look at force and momentum. Isaac Newton's second law of motion. The second law states that the rate of change of momentum of a body is directly proportional to the force applied, and this change in momentum takes place in the direction of the applied force. So what that means is that F equals the rate of change of momentum, P represents momentum, and momentum, if you remember from the first one, equals mass times velocity. So we're looking at the rate of change of mass times velocity with time. And calculus note 2. The differential of a product of variables, because mass and velocity are both variables, is equal to the first variable times the differential of the second, plus the second variable times the differential of the first. And so it looks like this. Force equals mass times the differential of velocity, m dv by dt, plus v times the differential of mass, v dm by dt. And we'll remember this one as equation 2. Now we're going to look at equating force with energy. From the work-energy principle, we had that E equals the integral of f ds. From the analysis of force and momentum, we had force equals mass dv by dt plus v dm by dt. Putting equation 2 into equation 1. So taking this expression for force and putting it into this first equation, we will get E is equal to the integral of m dv by dt plus v dm by dt times ds. And we multiply ds into the parenthesis, we get m dv ds by dt plus v dm ds by dt. We know that ds by dt is the rate of change of distance with time, which is known as velocity. So putting that into this equation, put in v for ds by dt, we get E equals the integral of mv dv plus v squared dm. And we remember that one as equation 3. From Einstein's theory of special relativity, we know that mass is proportional to the rest mass. This proportionality function is known as the Lorentz transformation and is equal to 1 over the square root of 1 minus v squared over c squared. And you can note from this that you can see why you cannot travel faster than the speed of light, because if your velocity v was the same as the speed of light, you would have 1 over 1 minus 1, which is 0. 1 over 0 is infinity, and so you would have to have infinite mass. And if you have infinite mass, you need infinite energy. And so it makes it impossible to go faster than the speed of light. Now this gentleman down, we know Albert Einstein, but this gentleman down here is Professor Hendrik Antoon Lorentz. He was a Dutch physicist who derived the transformation equations underpinning Albert Einstein's theory of special relativity. Squaring both sides of this equation, we get m squared equals m0 squared times c squared over c squared minus v squared. And that's just factoring out this parenthesis down here. So we can say that m squared c squared, multiplying this parenthesis up to the top on the left, m squared c squared minus m squared v squared equals m0 squared c squared. And it's important to notice that rest mass is constant and the speed of light is constant. So this expression is constant. Calculus note number 3. We want to talk about this time the differential of x squared. And the method is to put the exponent at the front, so it becomes 2x. And the differential of x squared is therefore 2x dx. And the differential of a constant is 0. And that's because constants have no rate of change. So what we have here then is, once again, we have a constant c squared times the differential of m squared. So we have c squared 2m dm. And mass times velocity here, both squared, are both variables. So we're going to have v squared times the differential of m squared. So we'll have v squared 2m dm minus, we have a minus at the front here, m squared times the differential of v squared, so it would be m squared 2v dv, and the differential of the constant is 0. And now we can divide by 2m. We have 2m here, here, and here. And when we do that, we have c squared dm minus v squared dm minus mv dv equals 0, and therefore c squared dm equals v squared dm plus mv dv, and this will be equation 4. So, bringing it all together, from equating force with energy, we had energy is the integral of mv dv plus v squared dm. From relativistic mass, we had c squared dm equals mv dv plus v squared dm. And as you can see, this expression here is the same as this expression here. And so combining these two equations and replacing this with c squared dm, we have that energy equals the integral of c squared dm. And then integrating, and remember when you integrate a constant, it's just a constant, so c squared can come outside. So it's going to be the integral of c squared. It's going to be energy equals c squared times the integral of dm, which means that E equals mc squared because the integral of dm is m. And that's it for this derivation and for this video. And I look forward to seeing you next time.